All right. But in this lesson, you will know how to describe how charged particle is forced magnetically when it travels through a magnetic field. Use your right hand to determine the direction of the magnetic force field and velocity. Calculate and determine the direction of the magnetic force acting on a moving charged particle, and calculate and determine the direction of the magnetic force acting on current with or wire with current flowing through it. All right. Foundational fact number 1 said this: moving charged particles create a magnetic field. Okay, you just kind of have to accept it. Like, we've observed it to be the case. It's a thing, and we have a right hand rule number 1 to help direct understand that, or like put that into how that's put into practice. Okay. Foundational fact number 2 says this: the charged particle is moving perpendicular through an already existing magnetic field, then it will experience a magnetic force that is perpendicular to both its velocity and magnetic field. Clear as mud. Fact 1 was moving charged particles create a magnetic field. You're welcome. Okay. So all I want you to do is just like capture that, and we'll talk about it. If a charged particle is moving perpendicular through an already existing magnetic field, then it'll experience a magnetic force that is perpendicular to both the velocity and the magnetic field. Okay. So let's figure out what in the world that's talking about. All right. If you were drawing this, I would just do the 2-dimensional version. So let's say we have a horseshoe magnet. And the magnetic field between the uprights looks like what from your magnet lab? Out of north and the south. Good with that? Now, I think we're just running out of letters. Like, there is no Latin or Greek root that starts with a B. It's just like, easy M. That's all right, B. Okay, so there's no logical connection there. That's your magnetic field. Okay, so this is our already existing magnetic field. This is our external magnetic field. And then what we're going to do is we're going to take a proton, a positively charged particle, and we're going to kick it through the uprights. We're going to shoot for a field goal. Okay. So it's moving this way, some velocity, positively charged. Two-dimensionally, that's looking like your circle with a dot. Okay. So you see how, okay, so this, you have a magnetic field going this way. You have a velocity going this way. See how these are perpendicular? That makes sense? Okay. So because of that, it's going to experience a magnetic force that is perpendicular to both the magnetic field and the velocity. To determine that, we're going to use right hand rule number 2. So each foundational fact has a right hand rule associated with it. Okay. There are variations of this right hand rule. The one I'm picking, I think, is the most consistent with right hand rule number 1. So in right hand rule number 1, what did your fingers represent? Tell your neighbor, what did your fingers represent in right hand rule number 1? There we go, Mega. The velocity. Yep. Okay. Your fingers are the magnetic field. Okay. In right hand rule number 2, your fingers are still your field. But now instead of curling them, we're going to keep your hand flat. Not curled. Flat. Okay. Your thumb represented what? Current. Okay. This will continue to be current if you have current flowing through a wire. If you have a single particle, it's the velocity. It's which way things are moving. You see that? Does that make sense? The connection there? Okay. So what we're going to do is we're going to stick our fingers in the direction of the magnetic field. Which way are the magnetic field lines going? To the right. So stick your fingers to the right. Okay. Here's a very strong, good advice, suggestion, recommendation, almost a requirement. This gets really complicated really fast. Okay, you'll be like moving your hand all over the crazy place. Once you pick something, lock it in, commit to it. Okay, in the vocabulary of Project Lead the Way, you're going to constrain it if you ever took any of those classes. Okay, so your fingers are going to the right, you're locking that in, you're committing. So now all you can do is pivot your hand like this, because your fingers are always pointing to the right in this example. Your thumb corresponds to what? Velocity. Which way is the velocity going? Circle the dot means what? Out of the page. You're looking at the arrowhead. You got a duck. It's coming out of the page at you. So your thumb's held like this. The force, the magnetic force, is the way your palm is pushing. Your palm is pushing up. Good with that? Okay. Notice that is perpendicular to both the magnetic field and the velocity. In math terminology, you have an X, Y, and a Z axis you're now dealing with. Three-dimensionally. Good with that? Okay. The exception is if this is a negative charge, if you had an electron being shot through. Your hand, you're still going to hold it exactly the same way. Your fingers are still going in the direction of the magnetic field. Your velocity is still going in the direction of velocity. Sorry, your thumb is going still in the direction of the velocity. The only difference is instead of forcing with the palm, you're back of the hand. So it's going to be forced down in the opposite direction. Okay. The way that I remember this, palm pushes positive. Palm pushes positive. If you get backhanded, that has a negative connotation. Back of the hand is negative. After that, questions there. All right, so this next part, we're just dedicated to learning how to use your right hand rule. Number 2. Yep. All right. What part of your hand corresponds with the magnetic field? Tell your neighbor. Put your fingers in the same direction of the magnetic field. Okay, let me just throw out this too. This is awkward. Just embrace it. All right. Everybody's doing it. Doesn't matter. Yes, it looks. It's okay. Okay. Like this is it's a tool that you have to use to be able to do this. Like it's just a thing. Okay. Just embrace the awkwardness. Okay. So fingers go up. Okay. What part of your hand corresponds with velocity? Your thumb. So your thumb goes which way? Coming out of the page. So lock your fingers. So right now, you can only do this. That's it. Okay. So your thumb, rotate, pivot your hand until your thumb is going out of the page. And this is going to be forced which way? It's positively charged, so it's going to be pushed which way? To the left. See how that's working? Palm pushes positive. I'll give you a little head start. See if you can start to figure it out. Okay. Heads up, it's negatively charged. So fingers go which way? Into the page. Okay. This corresponds with what? Thumb going to the right. Negatively charged. Back of the hand. Down. Being forced down. Good with that? Okay. All right. On this one, heads up. I did not give you the field. I gave you the force. I only need to give you 2 out of the 3 things. Okay. So pick one of those things and commit, constrain it. Like establish that direction and don't lose it. Anchor that. Make that an anchor point. Show your neighbor. Tell them what your conclusion is. I've never broken someone's wrist doing this. If it feels like it's going to, there's probably another way that's less awkward. Okay, what do you say? Okay, what part of your hand goes here? Thumb goes into the board. Okay. So now we're fixing this something. I know, man. Look. Okay. It's positively charged. So what part of your hand corresponds with this? Your palm. So you rotate it until your palm is going to the left. And now your magnetic field corresponds with what? Fingers. So your fingers are going which way? Down. See how that works? Okay. Stick your thumb in. Palm to the left. Fingers go down. I know, it's so fun. The test, I don't know when you're raising your hand for a question or when you're like, we get through it. Trick question. Correct answer is E, no force. A stationary charged particle does not interact with a magnet. Okay? It has to be moving perpendicular. Good with that? Give that one a shot. Pick one thing and commit to it. And then pivot your hand until it lines up. Tell your neighbor, show your neighbor.
I can't wait for this test to go around and to see everyone's gonna be like, oh, the force is down. Like you're gonna see what that is like. They're gonna be like, what are you saying?
Okay, correct answer is okay. So fingers are going out of the page. It's negatively charged. Fingers are coming out of the page. Circle the dot. Arrowheads, right? Circle the dot out of the page. It's negatively charged, so back of the hand is going down. So your velocity is your thumb. Your thumb is going to the left. Dangerous dinosaurs. Okay. I know this is. Listen, you're learning how to use the tool of the right hand rule number 2. Okay. It does not make sense. This is how it works. So you're learning how to do that.
Oh, girl. So, he's smiling, so it definitely is possible.
No, it's not. It has to be moving perpendicular.
Oh, you are right. Perpendicular.
Trick question.
I like these.
Tricky. Okay, so no force. Some part of it has to be moving perpendicular. Some part of the velocity has to be perpendicular. Okay. Oh, sorry, let me bring this to the light. Some of you told me that one of the questions on the pre-quiz had trig functions, but the video didn't have trig functions. I apologize. I will go through it. If you failed it because of that question, I will pay you back for that. Like, you will be able to pass. So, sorry. Some of you got it, some of you didn't. There's an assortment of different questions. Okay. All right. So, example problem. You got a particle moving, has 33, negative 33 microcoulombs, moving at 2,000 meters a second at 4 degrees through a 6.5 Tesla magnetic field. What is the magnitude of the magnetic force on the charged particle? Okay. So, so you have magnetic field times the charge times the velocity perpendicular component of the velocity. Okay. So to do this, I need the component that is perpendicular. So using this 40 degrees, I'm going to draw my components like this. That's my velocity parallel. And this is my velocity perpendicular. And this is 2,000 meters a second. You okay with that? I want the component of velocity that is perpendicular to the magnetic field. So what trig function am I going to use? I've got hypotenuse. I'm looking for the opposite. Sine. So I'm going to use sine of 40 is equal to velocity perpendicular over 2,000. Find that to be 1286. Is that legible? Can you read that color? Yeah, very good. Okay, so I've got magnetic force is equal to 6.5 Teslas times the charge of 33 microcoulombs, so times 10 to the negative 6th coulombs, still a thing. Okay, we're going to drop the positive negative sign on the charge in the math. So no, it's just straight up 33, not a negative 33. And then we're going to multiply that by 1286 meters per second. And we find that to be equal to 0.276 newtons. Okay, it's still a force. Put that in newtons. Good there? Okay, so that's the magnitude. That's the number. That's the amount. What I'm curious next about is what's the direction. So to determine this, we're still going to use our right hand rule, number 2. You're going to put your fingers in the direction of the magnetic field. Your thumb, check this out, do not put your thumb in the direction of the red arrow. put your thumb in the direction of the green arrow because that's the component that is perpendicular. Does that make sense? Do not put your thumb in the direction of the red. Put it in the green. Okay? And it is negatively charged, so which way is it being forced? Into the board. Into the board. Okay? Good? All right. All right, so if I was in your shoes, I'd be like, you are making this up. I want to see some proof here. Like, this is just crazy, random, abstract. Like, what? So, check this out. All right. That is a TV. All right. So, you should have learned this in chemistry, but I think they've changed the curriculum. Okay, well, I mean, there's reasons for that. So where does light come from? So light comes from so you have a molecule with electrons going around, and they have their different places, their different orbital positions. If something high energy, another electron or something hits that and gives it energy, it'll, in response to that, jump up to a higher orbital state. Okay? When it goes like, oh man, this is crazy, I want to go back home. When it falls back down to its original orbital state, it loses energy and emits a photon, emits light. That's where light comes from, just in general. The photon is light from the energy that it was released when the electron in the higher orbital state, in its excited state, falls back down. No, it just emits the energy, and that energy is it's light, and we call it a photon. Okay, it's energy, light energy that's emitted. Okay, so what's going on here is this is a cathode ray tube, and so what this is going to do is it's shooting electrons through this tube here, and in this tube there's some gas. I don't know what the gas is, but when the electrons go through there, they hit the electrons in the gas molecule and cause those to jump up. You can be excited, and then when it falls back down, it emits light. So you can see the path of the electrons going through here. Okay, so the electrons are going this way. Okay, now what I have here is a magnet. Okay, and this is the North Pole. This is the South Pole. So magnetic field goes out of north into south. Okay, I'm going to hold the magnet like this. So the magnetic field lines are going out of north into south. What I need you to focus on is the out of north part. Okay, so I'm going to hold it like this. So the magnetic field lines are going this way. The electrons are being forced this way. So you show me which way the electrons are going to be forced. Magnetic field is going this way. the electrons are going this way. Which way are electrons being forced? Show your neighbor with your right hand. Magnetic field's going this way. The electrons are being shot this way. Which way are electrons being forced? Here we go. Ready? Were you right? Goes up. Your hand should look like this. Magnetic field's going this way towards you. Thumb is going to your right. They're electrons, so they're negatively charged. Back of the hand, upward. If I flip the magnet around, so the magnetic field lines are now going towards me, going into south, which way is it going to be forced? Good at that. Okay. Now, this is an old school TV. Okay. Super thick. Deep. Okay. Why? Because they have a cathode ray tube in them. Okay. It has a Sorry. There you go. Here we go. It has a cathode ray tube in it. Has an electron gun. Shoots electrons towards the screen. The technology in here is pretty amazing. It shoots electrons towards the screen and it actually directs it across the screen. And it goes so fast, it actually makes a whole picture. It's kind of like flip books. But instead of, it's like, it's just. So if you've ever seen videos of old that have old TVs in them, you can see like a light bar going down. That is the frequency of the electron gun shooting across, captured by the frame rate of the camera. And so like there's a mismatch there. So that's why it looks weird like on old videos. So I don't know if you've ever heard the advice, don't take a magnet near a TV. That comes from these guys. Okay, that is a very familiar sound in my childhood. Okay. Great.
What causes that sound?
That's a good question. I don't know why that is. That's a good question. I got nothing. Okay. So check this out. This is like state of the art. Back. You just got a DVD player in the TV. Like this was big bucks back then. Okay. Now, so these electrons are being shot, directed by a magnetic field. If I take a magnet that has another magnetic field, I can distort their path. Okay.
Whoa.
Crazy. Whoa, that's so cool. And then, like after you get done playing with it, you're like, Dad's gonna kill me. Like, oh no. And so the high-end TVs actually had a demagnetizer function called degauss button, and you could press it and it'd take care of it. But if you're like left on your own, you're like, oh my goodness, I gotta figure this. And so you could like kind of like
move it out of the way.
Get it, like you can kind of like, haha, there it is. And then you don't get grounded. Okay, cool with that. But Does that make sense? This is messing with the path of electrons. Okay. There you go. You just get used to it. I mean, it's like it's TV. It's like.
You was either watch something or.
Okay. All right, give that one a shot. Tell your neighbor. Correct answer is downward. Holding your hand like this, negatively charged, downward. Okay. All right. Let's say we have an extensive magnetic field, like the whole wall is a magnetic field. Okay. Show me which way this proton is going to be forced. There we go with up. Okay. So if we let it run its course, it's going to be going this way now. That makes sense? Show me, because it's being forced up, well, show me which way it's going to be forced at this point. Finger's still going in, thumb's going this way, it's going to be forced this way, perpendicular to the velocity and magnetic field. Time goes on, it's now going this way. Which way is it going to be forced? Again, if this whole wall was a magnetic field and we let it run its course, what's this going to do? How's it going to move? What's the path? It's going to go in a circular path. Because how does the force, the direction it's being forced compared to the velocity? Perpendicular. What is a characteristic of centripetal force? Perpendicular to the direction of motion. So I could make you do some pretty cool problems. But I'll let you experience those in college. Okay? So magnetic force is playing the role of centripetal force. Good with that? Okay? So it's going to go in a circular path. So this animation is showing a positively charged object going through a magnetic field. It's going to do a spiral because there's some of this velocity initially was going parallel to the magnetic field. So it's going to do like a spiral. Cool with that? Okay. So some applications of this. One is a particle accelerator. This is like a subatomic demolition derby. So what they do is they have these crazy electromagnets, and this is actually in Chicago. It's called the Fermilab. They get a proton and they get it moving. This is the warm-up lap, and then they send it on the bigger one and get it up close to the speed of light. Then they raise this sacrificial molecule up, and then like bam, and then the wreckage, they capture that in a magnetic field. This is the path of the carnage. This was a positively charged particle. This was a negatively charged particle. And they're looking for undiscovered subatomic particles. Kind of what the point is.
Wait,
What is stuff made out of?
how do they know where to put like the molecule or whenever the proton's going that fast?
I mean, they know where to put it, it's just when it's going to hit. I think that's just there. And then I think they just redirect the proton with the magnetic field to hit the target. My guess. But it's in a magnetic field. So a more natural occurring phenomena is the Northern Lights. Okay, so this I have seen the Northern Lights, but never in Indiana. I think it was like North Dakota. There's also Southern Lights. I've never seen those, but I'm assuming you're going to be like tip of South America or like southern part of Australia to see that, assuming you never get to the Antarctica. So plasma is the fourth state of matter, solid, liquid, gas. Every time you go up a level, you're making the particles more energetic. Okay with that? So a gas state, the molecules are free floating. They're not bound. Okay. Plasma is the next state, and that's so much energy that electrons aren't bound to the molecule. They're like, and they're like free, like that's plasma. The St. Elmo's fire that you had, the purple fire coming out of your fingertip, that was plasma. Okay. The sun is made of plasma. Okay. So
the electrically charged gas is called plasma. The plasma drags the magnetic field further outwards. The magnetic field stretches and twists like a rubber band. And then the rubber band breaks. Several billion tons of plasma is hurled out from the sun. This is called a solar storm.
okay, so this is you got a lot of moving charged particles. Create its own magnetic field. Okay, that was the rubber band analogy.
An invisible shield, the Earth's magnetic field, deflects the storm. The magnetic fields couple together and create a funnel where the gas streams down on the daylight side of the pole. This is the daylight aurora. The magnetic fields stretch further back and couple together. The magnetic rubber band breaks, and gas from the solar storm streams along the magnetic lines towards the poles on the night side. This is the nighttime aurora.
Okay. So what happens is the charged particles from the sun get trapped in the Earth's magnetic field. And do you know at like a science museum, the big funnels they put coins in and they roll around and then towards the end it's like okay, so that's what's happened to the charged particles from the sun and the Earth's magnetic field. It's like spinning, and when they're doing this, at some point they crash into a gas molecule in our atmosphere, and it shoots an electron from the gas molecule up to a higher orbital state, and then when it falls back down, it emits light. And that's where the northern lights come from. So this is slightly fast forwarded. Like you can see headlights from cars. Yep, cool with that. I found this several years ago actually. This is up in Canada. So this is like real time. So I did not realize they move this fast. Kind of like smoke. Yeah.
Is that like all a bunch of teepees, or is that like?
Yeah, it's some campground, like Yellowknife, Canada. Well, that. So, got a worksheet due tomorrow.